Good morning. Today we are going to be continuing with our exposition on the stiffness method, where we're going to be looking at a few more examples. I'll look at one example and then I will essentially establish how to consider thermal stresses in the stiffness method. Okay? So today's lecture is on the stiffness method and we're going to be looking at examples. Okay? The first example was the one that I had presented in the last lecture at the end, which was this was the problem that I had solved in the last lecture. A, B, C, D. This was the problem that I had solved in the last lecture, and then I had said that instead of this member, so this member is now flexible, this member now becomes rigid. So this was the problem that I had given to you, that this is EI, this is EI, and this is rigid. Okay? So today we are going to look at this and see how, and this is a more realistic problem where the columns are flexible and the beam, essentially because it has these are normally monolithic with the slabs, and therefore these are T sections, and the EI values for beams are typically much larger than those of columns. So one of the simpler way to deal with it, when one member has significantly larger EI than others, is to assume that that is flexually rigid, because after all the rotations over there are going to be small and we might as well neglect it. Okay? Here note that the degrees of freedom are respectively, well, how many degrees of freedom do we have? Well, if we look at it, let's go through it. Okay? So this was the problem. How many degrees of freedom? It will still hopefully remain 2. The only factor that becomes that it is 2 is that this is a degree of freedom. Okay? And think about it. Can you have a rotation at this point at B without this? Well, think about it. If this rotates, then this has to go up. If this goes up, then the only way this can go up is by this moving, and if this moves, it moves horizontally. So therefore, the 2 degrees of freedom actually are this and this, but this is no longer a degree of freedom. So let us write down, prove to you that this is actually a single degree of freedom system. And for that, let us go through the steps. How many joints? 4. So 4 into 3 is 12. Okay. Then how many restraints? 1, 2, 3, 4, 5. So 5 restraints. How many constraints? 1, 2, 3, 4, 5. Okay. So that means there are 2 degrees of freedom. Okay, but one of them happens to be this end rotation, where anyway we know the moment is there. So I have only 1 degree of freedom, essential degree of freedom. There is a second degree of freedom here, which I don't want to find out the displacement right now. Okay, so this goes as a single degree of freedom system. And how do we solve this particular problem? Well, let's see. First and foremost, AB and BC are the AB and CD are the members. So for AB, what is it? The member is fixed at A and continuous at B, and therefore V is equal to theta AB, theta BA. Okay? That is V. Okay, and what is S? S is MAB, MBA. Okay, fixed end moments AB, fixed end moment BA, which is equal to S0, S0 is equal to 0, 0, and KAB is equal to 2EI, and this is 4 meters, so this is 2, 1, 1, 2. Okay, so this is your member AB. Now BC is a rigid member, and therefore you do not consider BC as part of the members. Okay, and therefore next consideration would be for CD. CD is continuous at C, so it is fixed, and at D it is hinged. So this is C, D, okay, and so therefore V in this particular case is theta CD. S is equal to MCD. S0 is equal to 0, there is no load, and KCD is equal to 3EI by length, which is 5. Okay, so I have done I found out for each of the members. Now I need to find out how to get the member degrees of freedom related to the kinematic relationship between the member degrees of freedom and the structure degrees of freedom, for which I have to do the kinematic relationship. And therefore this particular situation, if we look at it, we have, now note that this is the rigid one, okay, and then we have this which is continuous, and here I have pinned. Okay, so if I give it a unit displacement, so R1 equal to 1. So R1 equal to 1 would imply that this would go here. Now this point would also move here, but it cannot move only that way. It has to move perpendicular to this, and this perpendicular is, if this is 1, this is 3 by 4, so this is 5 by 4, and the displacement pattern looks like this. This, if it has gone here and this point is here, the rigid member is going to remain straight. That is the most important. What is this angle? This angle is equal to 3 by 4 upon 1 upon 4, so this becomes 3 by 16. Now once that happens, note that if this is the thing, this also has to move by 3 by 16. So the tangent becomes like this, and this member comes like this. Note also that this tangent also has to rotate, because this has rotated, and therefore this goes this way, and these rotations are 3 by 16. This rotation over here is also 3 by 16. So your rotation, this is hinged, and what is the, we are always taking theta from the chord. Okay, so this angle, since this is 1 and this is 4, this is going to be 1 over 4, this is going to be 1 over 4, and this is going to be 1 over 4, 5 by 4 upon 5 because that is the length of the member, and so this here is going to be 1/4. So if we look at it, then what is, and since this is my only this thing, A B is going to be equal to, AB is 1/4, BA is 1/4 plus 3/16, that's from the chord to the tangent. So if you have that, that is 7/16, and note that these are anti-clockwise, so they are positive, so you have 7/16, and ACD is equal to 3/16 plus 1/4 from the chord, and this is also counterclockwise, so this is 7/16. That's it. Okay. Now this, note that this load over here, how much has that displaced by, that point, the central point, how much has it displaced by? The central point, by the way, has moved by 1. So this, how much is this? This is going to be half of 3/4. So this is going to be 3/8. So the point, the load point has moved up by 3/8. This is going to play an important role in our calculations a little bit later. Okay. So now I have computed the AAB. So all I have to do now, for each member, I have to compute the note that in both the cases the fixed end moments are 0, and therefore all I have is directly SAB is equal to AAB into KAB into R, which happens to be a 1/1. So if I look at this, this becomes 2EI upon 4, 2, 1, 1, 2 into 1/4 into 7/16. Okay, so this is equal to, I'll make it 2/4 plus 7/16, 8/16, so this becomes 15/16. So EI upon 2 into, this is going to be 15/16, and this is going to be 14/16 will become 7/8. 7/8 plus 1/4 is going to be 9/8. Okay, so this is into R1, that is SAB. Okay, so therefore the contribution to KAB is going to be equal to 1/4 7/16 into EI upon 2, 15/16 into 9/8. So if you look at this, this becomes 63 upon 128, and this becomes 30 upon 128. So 63 plus 30 is 93 upon 128. So 93 upon, so this is going to become 93 EI upon 256. Okay, because 128 into 256. So that is KAB. Now let us look at CD. CD is going to be SCD is going to be equal to KBC into ABC into R, which is going to be equal to, what is it? 3ei upon 5. Okay. So, it's going to be equal to 3ei upon 5 into ABC is 7 by 16. So, this is going to be equal to 21 ei upon 80 into R1, okay, and KBC, which is going to be A transpose. A transpose is again the same. So, it's going to be 7 by 16 into 21 upon 80, which is equal to 147 upon 1280 EI. So, when we add both of them up, what do we get? We get this, the following. R is equal to K into R plus A summation transpose SI0 plus blah 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 blah. Okay. Now, the major point to be noted here is that there are no SI0 and NI0, so we don't need to worry too much about that. So, therefore, the K is going to be equal to 5, this is going to be 465 plus 147. So, it's going to be 465 plus 147 upon 1280 EI, which is equal to, if you look at it, this becomes 612 upon 1280 EI. And if we look at this, this can go through by 4. So, this becomes equal to 153 upon 320 EI. That is K. Okay. And what is R? How do I note this is R prime? How do I get R prime? For R prime, note that in the previous case, even though in this particular case I have a load over here which looks like a load which is on a member, but note that BC is not a flexible member, and since BC is not a flexible member, any load on a rigid member is considered equivalent to a nodal load, and therefore, since the effect is not on a member, here the members are AB and CD, okay, since those are not there, therefore, you have to consider this not as a member load, because BC is not a member. Note, BC is a rigid member, and therefore, it is not one of the considered members. What we have to do is find out the work done by the 100 Newton, and this 100 is going to do negative 3 by 8. So, the work done would be 100 into negative 3 by 8, which basically becomes 75 by 2. Okay? So, this then says that R1 is equal to minus 75 by 2 multiplied by 320 upon 153 EI. So, this is equal to this, whatever this value comes out to be. Okay, I am not going to compute. So, that is my R1. As soon as I know my R1, I know my deflection pattern. And since I know R1, I can also find out what MAB and MBA and MBC are. These can be immediately evaluated, okay? And once I evaluate those, for example, what is MAB equal to? MAB, let me just put it down, MAB AB is equal to 15 by 32 EI into minus 75 by 2 multiplied by 320 upon 153 EI. EI cancels, 320 cancels 10, 10 cancels 5, so it's going to be equal to minus 75 squared upon 153 kilonewton meter. MBA is equal to 9 by 16 EI multiplied by minus 72 320 upon 153 EI. EI cancels out. This goes 20, this goes 10, and so what we have is 775 into 9 becomes 675, so 6750 upon 153 kilonewton meter. And MBC is equal to 21 EI upon 80 into minus 75 by 2 multiplied by 320 by 153 EI. EI cancel, this goes 4, this goes 2. So what we have is 1575 into 2, 1575 into 2 is equal to 3150 upon 153 kilonewton meter. So therefore, these are my MAB, MBA and MBC. Now once I have found out my R1 and MAB and MBC, MBA and MBC, now how do I solve this problem? Okay, displaced shape, no problem. All you have to do is, this is my displaced shape, only thing is that it will be in the opposite direction. So this will come down, this will go in this direction, this value I know, and therefore I can find out all the other values automatically. Okay, and that's what you would expect, that since the load, this point would come down, and therefore this would have to move in this direction and in the opposite direction. Now on to the support reactions and the bending moment diagram. Okay, so since now I'm just going to again put it here. What do I know? I know what MAB is. This is going to be minus, so this is going to be clockwise. Okay, and clockwise approximately about 73 kilonewton meter. This is what it comes out to be approximately. Okay, this is also going to be clockwise, and this is going to be equal to about 40 for 1560, so it will be about 44 kilonewton meter. I'm giving you approximate numbers. I'm not. Now this one I don't know anything about. Okay, but this one I know. What is it? This value is going to be equal to, again clockwise, so this is going to be clockwise, and the value is going to be approximately 20. So it's going to be 20, so this is going to be 30690, so it's going to be about 21 kilonewton meter, 20 point something. Here this is 0, I know that this is 0. Okay, the displacement here is going to be 0. Okay, now let's go through the steps. See, this I know nothing about, because this is not a member. This is A, this is B, this is B, this is C, this is C, this is D. I don't know anything about. But you see, there is no moment at this particular point. Okay? So since there is no moment at that particular point, for BC we can find out the member end moments purely from equilibrium. Okay? So since I have 44 over here, from equilibrium this will have to be 44. Here again from equilibrium this has to be 21 kilonewton meter. This has to be 44 kilonewton meter. Okay? So I know that these are going to be the moments. Okay? Now what else do I know? Since I know this, I can find this. Okay? So I can find this and this. And since this is 117 divided by 4, I'm again doing approximate numbers, is going to be equal to 117 this way divided by 4 is going to be equal to 29. So I'm just doing basic 29 kilonewton meter, 29 kilonewton meter. Okay. Now once I know this, again this has to be 29. Now note that there is this 100 force. So this has to be this way, 29. So therefore here I need to have a force this way. Since I have a force this way, this is going to be 29, and therefore I am going to have a reaction here which is equal to 29. Okay? So I know this reaction. Since I know this reaction, and how much is this going to be? This is going to be in this fashion. So this 29 into 4 is 117, this 117 plus 21, okay. 117 plus 21 is going to be equal to what? 117 plus 21 is going to be 138. 138 divided by 3, because this one is this way, so this one has to generate this way. So it's going to generate this way, and this is going to be equal to 138, 117 plus 21, 138 by 3. 138 by 3 is going to be equal to 138 is going to be 46. So this is 46 kilonewton. Now since this is going to be 46, by definition this has to be equal to 46, and if this is 46, this has to be equal to 54. If this is 54, then this has to be 54, and therefore this has to be 54. Now the question is, does this check? Let us look at this. Okay, what we generate over here from the 100 is 50-50, but for this it's going to generate an additional one. So this is going to be equal to 44 and 21 is 44 and 21 is going to be equal to 65. 65 divided by 4 is 15. Okay, so let us look at this again, because there has to be equilibrium. Okay, without equilibrium you cannot satisfy this particular problem. Okay, there is no moment here. So if I take moments about this point, this 46 into 7, okay, has to be equal to, so let us check, let's go back and check what we are doing here. This is 117 this way. Yeah, okay. So essentially what happens now is, therefore if you look at the reactions are this way. The reaction over here is 29, 54, 73. The reaction here is 46 and 29. Okay. So I found out all the reactions, and once I know these, I can draw my bending moment diagram very easily. Okay. So I think this particular example was being presented to you essentially for the last point that I wanted to make as far as load effects were concerned, that if a load is on a member which is rigid, then it is not a loaded member, because BC, which is a rigid member, will not have any effect, and we have to consider the equivalent load on the left hand side. Okay? So I hope that after this you shouldn't have any problem solving any applying the stiffness method for the solution of any structural problem. Okay? As far as we have only considered effects of loads on the structure. Now let us look at certain other effects now, and the only other effect that I am going to spend any time, note that support settlement is not a major problem in this particular case, because all that means is if there is support settlement, that means there is a degree of freedom corresponding to that support settlement direction. Okay? And the only thing that happens is that we do not know the reaction at that point, but we know what is the left hand side, I know the displacement. Okay, so I can always solve for it, because after all I just get one additional degree of freedom, and that degree of freedom I just need to solve it to be able to get this thing. Okay, so now what I want to consider is the last thing, which is how do we consider temperature in structures. Okay, and that is going to be in the stiffness method, because we already know how to consider it this when you use the force method, the flexibility approach. Okay, so let us now move on to that quickly, and once we know temperature, how to consider temperature, we will have understood the complete concept behind the stiffness method. So let us now look at how to consider stiffness method. And again, since it's a member load, I'm going to first consider how to consider it. I'm going to first talk about how to consider it at the member level, and once we consider it at the member level, then considering at the global level becomes a trivial issue, because after all, again, all it does is that S becomes KAB-AAR plus SI0, where 0 is the fixed end moment. So all I need to find out is for temperature, how do I compute the fixed end moment? Okay, let's go back. So what we have here is, let me review the situation as we had already dealt with it earlier. So let me see what happens. Let me take a situation where both the top and the bottom, and note that here, since we are only considering flexure, okay, we are going to assume that the neutral axis does not suffer a temperature differential. If it does, all it means is that there is an axial deformation in the member, and that's all there is to it. Okay, I'm not going to go into the details of that right now. So let us consider the situation where you have delta T. This is the top fiber has delta T, and the bottom fiber has delta B. We've already seen that this gives rise to a curvature beta, which we defined as alpha into delta T bottom, delta T top, 2 alpha into D upon D, where D is the depth of the beam, the difference between the top fiber and the bottom fiber. Okay, this is D, to the depth of the beam. Okay, we had already done this, and we saw that this gives rise. So due to this curvature, you're going to have a theta, and theta AB. This is A, this is B. Theta AB is equal to minus alpha now this is length L, so it's going to be alpha L upon d, and theta BA is equal to alpha these I have already established in the force method and the flexibility approach that we looked at earlier. Okay, now this is my theta AB and theta BA due to the curvature. This is assuming that the neutral axis delta t at neutral axis is equal to 0. If it isn't, then all it does is that in additional to this, okay, if delta TNA is not equal to 0, all that means is that in addition to theta AB, we also have a delta AB, where delta AB is equal to delta TNA into L. Okay, so that's all. Okay, what does that mean? But then you see, our structures that our basic member that we have is this. Then I'll talk about the modified member a little bit later. This, and here we have delta T and delta B. Okay. Now, how do I compute the fixed end moments, as well as in this particular case, if there's an extension, you also have these forces that come into picture. Okay. So therefore, what is that equal to? Then you can see that this, we find out the fixed end moment exactly the way we find out that remember that all that we knew is that this one may be due to a load or may be due to a temperature. How did we compute the fixed end moment? Look back, think back at how we computed fixed end moments for members, and you will see that all we need to do is find out the fixed end moment such that the other direction is going to give you theta minus of theta AB and theta. So fixed end moment at AB and fixed end moment at BA are going to be equal to minus, okay, into Ka. So Ka is 2EI upon L 2, 1, 1, 2 into theta AB and theta BA. Okay, and so these are my FEM AB and this is my FEM BA. This is my P, this is my P. We can show that P is equal to nothing but this is minus because it is opposing, but then I'm just proving it. This is equal to EA delta TNA. Okay, sorry, delta AB, EA by L into delta TNA L. So LL cancels. So this becomes EA delta TNA. Okay. So this is, I'm not going to go into this, but let's see what this comes out to be. Okay. This comes out to be equal to, I'm going to plug in the values of this thing, and therefore fixed end moment AB is equal to minus 4EI by L into theta AB minus 2EI by L theta BA, but then theta AB is minus of theta BA, so this becomes equal to 2EI by L into theta BA, which is equal to alpha delta TB minus delta T L upon D. So L cancels, and so this becomes 2 EI alpha upon D into delta TB and delta TT. And if you look at the other one, this was going to be fixed end moment at BA is going to be equal to minus fixed end moment at AB. Okay. So these are the fixed end moments due to the rotation. Okay. So now if we have this kind of a situation, how does this translate into a problem that we can, how do we solve this problem? So let me now just take you through the problem that we solved last time, and instead of the load of 100 kilonewtons, I am going to put it equal to temperature differential of 100 kilonewton. Okay. So therefore, let me just go through with this. So let me take the problem that we were talking about. I'm looking at the last week's lectures problem. So this was the problem. Okay, so EI rigid A, B, C, D, and now the only thing that I have over here is that this is minus 20 degrees and this side is plus. The reason why I am doing this plus and minus is to ensure that delta NA at 1 is equal to 0. Okay. So now, so how do we solve this particular problem? Well, 2 degrees of freedom, without going into the detail, we've done it already, R1, R2. All that happens is, you see, AB is still a member without any loads. Okay, so I'm not going to go into the computation of AB. The only thing that happens in BC is that SBC 0, in the previous case we computed it for 100 kilonewton load at the center, and we computed PL upon 8, PL upon 8, and went through with that. Now in this particular case, all that happens is that SBC is equal to what we've already computed. That is going to be MBC MCB is equal to, now note that in this particular case we can take alpha equal to 1.2 into 10 to the power of minus 5 meter per degree centigrade. Okay. So if we plug that in, we get that the fixed end moments, these are the fixed end moments, are equal to 2 into EI into 1.2 into 10 to the power of minus 5 into delta bottom minus delta top is 40 divided by d. This is my fixed end moment. Note that what are the units of this per degree centigrade? This becomes a dimensionless value. What is this? Newton meter squared. Newton meter squared divided by meter is Newton meter per radian. Newton meter, and that is the units of the moment. Okay, so there's consistent units, and this one becomes 2 into EI into 1.2 10 to the power of 40 upon d. So the only thing that happens is that in this particular case, instead of the 100 kilonewton force, you essentially have this moment, and therefore once the moment, I can plug in a value of EI and D. I have not put that in. You'll actually get it in, let's say if the units of EI are in kilonewton meter squared. Okay, let me say that EI is equal to 1 into 10 to the power of 5 kilonewton meter squared, and let me say that the depth of the beam is 50 centimeters, so it's 0.5 meters. Okay, if you plug that in, we'll put those values in. What you get? You will see that this is 1 into 10 to the power of 5, and this is 0.5, 1 into 10 to the power of 5. What you get is 48 into 2, 96, so you get 128. So these become 128 minus 128 kilonewton meter. And once you have 128 kilonewton meter, then all that you have to do is that this is my SBC. Everything else continues in exactly the same way. You compute. So what are the steps? Once you've done this, so you have both for AB and BC, you have KAB, AAB, KBC, ABC. Okay, and so this, the SI is going to be equal to KI, this is into AI. Where do I get AI from? I get AI from the kinematic relationship. I am not going into the details of the kinematic relationship because I've already solved this problem. The only difference between this problem and the previous problem that I have already solved in the last lecture is that instead of the 100 kilonewton force, I've just considered it to be a temperature. So therefore, there is no difference in A, Ka, and all of those kinds of things. KAB, AAB, KBC, ABC, all these are identical to what we've already. I'm only trying to show you how you will, what effect the thermal has. And I've already shown that the only way to consider thermal is to compute the fixed end moments. And I've already computed the fixed end moments. And all that happens is once you have this, this becomes this. Where this now includes effects of temperature, which means thermal stresses. Okay, so this includes the effects of temperature. So this I can always get, and then I can also get ultimately this, which is K into R. Note that there's no change, and summation AI transpose SIO. Note now that AI bar transpose NIO. This is 0 for thermal load. Because when you have a thermal load, you do not have any additional reaction. There is no reaction. There is only a equal and opposite moment that is developed at the fixed ends. Okay, and those are essentially to account for the curvature that comes into picture because of thermal. Okay, this of course includes thermal load, no difference for thermal load. Okay, so the point that I am trying to make is, and this is of course no effect of thermal. So therefore, if you look at this particular problem, okay, the only part where the thermal effects at the member comes into picture is only in this, which is the fixed end moment, and that we have already included in our formulation. Okay? So therefore, if you really look at it, all we have to do right now is, if you to review it, that wherever you have a temperature load effect, okay, and you are looking only at the flexural part of it, all it does is that you have to account for it in the fixed end moments, and for fixed end moment I've already given you the effects. This is the fixed end moment, where this is the temperature differential at the bottom, temperature differential at the top fiber, and this is the depth of the beam, this is the coefficient of thermal expansion, this is EI. Okay, that's all there is to it. Of course, there is an additional effect here, but if EA is equal to infinity, then all you have is that this effect has no effect whatsoever. All that happens is that you have an expansion, and therefore you have an additional displacement because of the expansion of the particular member. There is no effect on the structural composition as such. Okay, so much for the displacement method and the stiffness method, which is the matrix displacement method. And I hope that over the last many lectures I have solved quite a few problems in the stiffness method, and at the end of this I hope you shall be able to apply the Stope reflection method, the displacement method, the stiffness method, which is the matrix approach to the stiffness method. Thank you very much, and from the next lecture I'm going to look at a completely different topic, and that is influence lines, which is equally important. By the end of this lecture, I hope you will be able to solve any planar problem, planar frame problem, using either the force method or the displacement method, as well as both their matrix methods associated with them. The matrix method associated with force method is called the flexibility method, and the matrix method associated with the displacement method is known as the stiffness method. Thank you and bye.